Hi, everyone. My name is Marina. I'm a data scientist with GetYourGuide. I work together with Jean on the growth data products team of GetYourGuide. Both at GetYourGuide and prior, I've been working a lot with NLP projects and also most recently with LLMs. And in general, the field of NLP is super interesting to me. And I also myself am super fascinated about how to utilize all the recent breakthroughs in a more cost-efficient way. So yeah, I think this topic of this talk is super relevant, and I'm really glad joining you today to discuss this. I'll also learn from you from our discussion as well.
Yes, just chiming in. Hello, Jean. I already introduced. I'm also working at GetYourGuide with Marina in the growth data process and in the machine learning platform team. I have an engineering background. I'm also one of the organizers of the MLOps community Berlin, and we do our job there in GetYourGuide is pretty much to put like data products into production. So putting these machine learning systems to work 24/7, and this is super kind of relevant. Also being able to tie this to sort of more meaningful topic on like nonprofits and so on. I'm really kind of burning for the topic. So thanks for listening, folks. We'll hand over back to Marina so she can introduce us.
Yes, could you switch the slide, please? Right, so Julia already gave a great motivation for why this is relevant now, especially for this DSSG. But just to give an overview, as you all already know, over the last few years, there have been some great advancements and NLPs, especially around LLMs and generative AI. And that also meant that the models were keeping to get bigger and bigger. And actually, over the last 5 years, the biggest models became 15,000 times more big parameter-wise than they were before. And that, of course, makes it a lot more computationally expensive to both, could you switch the slide, please, Ran? To both train the models and also use them for inference. And even a single fine-tuning run of an LLM model, of course, depending on your settings or the hardware you use, but it can easily cost more than 100 euros per single run. And this is especially the challenge for students and NGOs. So it's important to consider different options for cost reduction and optimization. Next slide, please. So first of all, it's important to figure out whether for you it's more cost beneficial and also the development time more optimal to go with a closed source or an open source solution. And when talking about closed source, I mean mostly OpenAI and ChatGPT in particular. And it can be a good option if you want to build a quick proof of concept. Your expected number of requests if you go for production is low, and that data privacy is not a concern. But if you do have a lot of requests expected and like more than 100,000 per month, for example, and maybe you're dealing with more sensitive data, it's best to go for open source solutions probably, because even though the upfront inference cost might be more, but it scales better with the amount of requests. So next slide, please. Both options can be good, but to emphasize more open source, great resource is Hugging Face, which all of you I'm sure know. It's has most open source transformer models available there. It also provides free model serving, dataset versioning, model versioning, sorry, not model serving, dataset versioning, data apps serving, and even some model training, though with low resources. The model serving, though, is paid, but I think the main advantage is the transformer library and all of the other libraries around Hugging Face, which provides great standard and abstractions to build on top of. Next slide, please. So I think one important thing to consider is, first of all, model selection and how complex do you actually need to go. Sometimes it's a good idea to take a smaller, maybe older model that's not as accurate for your task than the most recent one, but it still performs well enough and gives you a great saving on cost for compute and storage. Here are some examples for some standard NLP tasks. So of course, it's not an exhaustive list, but yeah, one thing to start is like maybe you don't need the biggest model. Yeah. Next slide, please. So when you want to optimize costs, we can go at it from infrastructure optimization, but also from the model training optimization. And for that, for example, when you're actually training the model, it's important to validate your approach first and understand your data on a very cheap compute, like only using CPU or cheaper single GPU for shorter periods of time. Starting simple with understanding the architecture that you want to use, getting that right, validating the approach on only a sample of data, just understanding that your training goes as expected, for example, and not training, not going for marathon training right away on a big model, only to figure out that the training stuff was wrong and you need to restart everything again. And when we go for actual model optimizations, could you also switch for the next slide, please? The important approach here is to take use of model compression techniques. These ones on the slide, quantitational low rank adaptation, pruning, and knowledge isolation are not the only ones that exist, but I think these ones are more commonly used. And a lot of these methods are implemented in either PyTorch, TensorFlow, or Hugging Face, or related libraries, and are quite easy to implement, and they allow to develop models that are faster and cheaper for training and inference, and also have smaller storage requirements. And all of these methods can be used in combination with each other. They're complementary, but there's always a balance for them with a trade-off, like how much you are willing to sacrifice the performance quality, because a lot of them do lead to the sacrifice to save on the costs. So first, to go to a little bit in more detail for quantization. So quantization is compression of the model for compression the representations of weights and activations by representing them with lower precision. So instead float 32, going for float 16, int 8, or even int 4, etc., even int 1. It significantly reduces memory requirements and also reduces computational costs, like it makes the model faster. It can be applied post-training, which is much easier, but it can also be applied during training. This is a bit tricky because quantization makes the model harder to converge. In general, with quantization, it's a little bit riskier than other approaches, so it's very effective because it might not prevent you from understanding what's your actual potential of the model is, because it does have impact on accuracy. So with quantization, it's important to understand what is like a good baseline for your problem, and then with knowing the trade-off, using it. And quantization is implemented in PyTorch, TensorFlow, Transformers, Accelerate library that's often used with transformers, and so it's available and implemented. Next is low-rank adaptation, which is several techniques that are implemented in PEF library, which is part of Hugging Face. It's, or at least often used with Hugging Face models. It is specifically a set of methods for working with large language models and reducing their size and reducing the memory requirements and speeding up the training. So first one, low-rank adaptation of large language models, LoRa, freezes the weights and injects trainable rank decomposition matrices. So as on the image, basically you're freezing the weights of the pre-trained model and only training the B and A lower rank matrices, updating only the lower rank matrices, which makes the model, I think, if I remember correctly, the storage requirements are 3 times smaller, and the compute is also quite a lot faster. And another approach is QLoRa. It's even better optimized, though of course it does affect quality a little bit more. LoRa almost does not affect quality. So QLoRa also adds a 4-bit quantization on top of LoRa, so the pre-trained model is loaded being quantized, but then the updating of the weights and the training of the decomposition matrix is happening in full precision. Yes, as I said, both are implemented and are very easy to use. We even have a code snippet at the end of the presentation for that, which I will show. But yeah, the next technique is pruning. Pruning is very effective for compressing the model, and it also is quite effective for making the models faster on inference. To give you a range of how much smaller I can make the model, it's like at least several times. It really depends on your on the model that you're pruning, how much you want to prune, but it's quite significant. Pruning can be applied. So pruning gets rid of the portion of the weights and connections that not as important for the model performance. That is usually applied post-training, though it can also be iterative. So you're trained, then you prune, then you continue to train. And it is implemented in PyTorch, TensorFlow, Optimum, and a code snippet of how like unstructured pruning for weights in PyTorch can look like is here. So it's, again, quite easy to use. There is, if you apply pruning post-training, the reduction of accuracy of like performance quality is quite low. So it's a very effective technique to use. Next, we have knowledge distillation. This one is used a bit more, or a bit less, sorry. It's because usually you do need to train the initial big model. And the idea here is that you are using the bigger model, a teacher model, to transfer the knowledge, to distill the knowledge to a smaller student model. And a student model learns to mimic the behavior of the larger model. The knowledge distillation can happen in different ways. So it either can try to mimic the outputs of the model, like the predictions itself, or the weights, or the mapping between several components. So it can be set up in many different ways, but in general, you're basically passing the knowledge from a bigger model to a smaller model, and therefore, at the end, you have a model that's much easier to use for inference, and in production requires much less storage. And popular example of that is DistillBird, which is 40% smaller, 60% faster than the original, and all that while retaining 97% of performance on natural language understanding tasks. And now over to Jean to talk about using hardware cost efficiently.
Thank you, Marina. Yes, so let's take a look into the hardware part right now. So the first thing, going back to first principles, like which costs do we need to take to basically put these LLMs into production? And take basically three axes. Basically, compute. One needs compute access for training and for serving. Training is the one that requires the kind of bigger hardware and yeah, quite significant costs can come from here. But actually, in practice, at least in the use cases we deal with, the bottleneck of costs is usually on serving, because serving requires sort of similar hardware, but it has to be running 24/7, so that gets very expensive very easily. Like to give a data point, like to put one model serving into production 24/7, like with sort of fallbacks, using only CPU is easy to get a bill of 1,000K per month. While training can also get to this level, but depends on the recurrency of training, basically. Data storage, on the other hand, is kind of orders of magnitude less expensive in a cloud provider, so I won't focus too much on it on the presentation. The last kind of constraint is time, human time usually. So basically, all of these optimizations that Marina also hinged on, all of them require kind of some time to integrate, to do it correctly, and so on. So there's a lot of trade-offs here, choosing the right methodology for the resources we have in hand. You probably hear my baby in the background, and yeah, I hope that's fine for you. And yeah, and let's continue. Yeah, so I wanted to hinge a little bit in local machine, though that's not the main focus of the presentation. So local machine is great for so many things. To get started with something new very fast. For instance, nowadays you can have very powerful machine. If you have like a M1 MacBook Pro, that kind of that matches the performance of like basically very big kind of GPUs. So it's very powerful and can be leveraged. Though there is also, yeah, many other constraints and cons on it, like hardware compatibility is a pain. You probably experienced like this Python issues with like the ARM architecture since the migration to 2 years ago. It's like
Ja, ich versuch's gerade, es tut mir leid. Ja, es tut mir echt, ich versuch's gerade.
Okay, maybe somebody needs to mute there, but I will continue. And yeah, so hardware compatibility can be a pain. Large data storage is also, if you have really big data, you cannot use your laptop for that, and then processing that is also tricky in your machine, and it's much less collaborative, right? So you cannot basically just jump in each other's notebook if they are in their own machines. So let's take a look a little bit further into the cloud. So I'll start with the compute part and understand a little bit more the hardware is available. So these are kind of all GPUs that are popular, and you can find kind of in notebooks in the cloud. So T4, maybe the most popular one, is a 16 gigabytes machine, is very optimized for inference. You can find it both in Kaggle and Colab for free. Then there is like bigger ones, for instance, the V100 with 32 gigabytes is a older generation GPU compared to the others. So also means it's less energy efficient. Also found in Colab. And there is P100, which is much faster than the V100, around 3 times, and it's also smaller. So also hinges that memory capacity does not necessarily correlate with kind of processing speed. You can find it in Kaggle. If you go for Colab Pro, then you can find also these A100s, which are very popular and kind of top performance level. Yeah, the 40 gigabytes version is available in Colab. Then moving on, taking a deeper look into these options like notebook providers and training infrastructure. So there's Colab, there's Kaggle, there's SageMaker. They have different free tier kind of options. T4 is in all of them. They have also different upgrade paths, right? SageMaker, you have to start paying AWS. Kaggle, you have to go to Google Cloud. In Colab, interestingly, there is like 2 options, Pro and Pro Plus. The Pro Plus is very interesting. Personally, you can pay $50 a month and you have access to 800 machines that are really kind of top notch. Yeah, all of them also have trade-offs, like you can in Colab you can lose connection. They don't guarantee you 800 as always. So yeah, if notebook restart, you also lose the data. In Kaggle, there is a limit of hours of week per kind of for compute. I think it's 30 hours a week. So, but if you use also this services kind of one as the fallback for the other, can work very well, and you can always have access to kind of GPUs. And with that said, let's talk a little bit about picking the right hardware. So here I put some examples of like common LLMs and what are their requirements. So usually training is more hardware demanding. It requires more RAM, usually because like if you're using add-on optimizer, for instance, there is a lot of kind of states that variables that it holds to kind of for each parameter that you have in your model. So that kind of increases the size of the memory requirements substantially. But if you start simple, like with BERT, you can do everything in your CPU with RAM. For inference, if you want to kind of pick the right hardware for inference and be very efficient, just 400 megabytes is what are the model weights, and you can do basically everything with that. Now, looking to Llama, which are kind of the, let's say, the most famous open source models, there's the 7B, 13B, and 70B options. The 7B, the tri-level one, you can basically fine tune it with T4s using LoRa with 4-bit precision. There is also this interesting project, Llama CBP, that the further optimizations, you can easily do that, fine tune it also in a MacBook Air. Regarding inference, so to serve this model, a T4 with 16 gigabytes and 16 bytes quantization can do it also. If you go to the most kind of extreme, like the 70 billion parameters, it classically kind of without optimizations, you can run on 8 A100s for training and 4 A100s for inference. But then quantization here plays this huge role. You can really kind of go to T4s, 8 T4s, using int4s and double quantization for training, or like A100s at 4 bits, or even like if you have a computer with CPU and 64 gigabytes of RAM at 6 bytes quantized, you can run Llama 70B in your machine. Yeah, here there is a formula on how to kind of estimate how much you need on memory for your LLM. The source is here, so you can also go for it. So yeah, last thing I want to say about this is, one thing is the memory requirements, right? The other factor is like the time of the person that is time of compute. So if you try to, for instance, fine tune in your machine a 7 billion model in a MacBook Air, even if you have the resources, it might take like months to do it for the amount of, if you have a big data set. So going for hardware accelerators, it's really important. And finally, let's talk about going to production. So I'm very much deep into MLOps, and that's a dear topic for me. So first thing about going to production is maybe you don't need to. Like, you can basically get the same hardware you are you're training your model, and basically get the data that you need to do inference with, and run the model through it and save the results in a file in a table. That's kind of a golden standard for us, as also in GetYourGuide, is that saves so much time if you don't need to kind of keep something running to do your predictions all the time. So yeah, it's so much more cost effective in price, but also like in resource, in people, like a data scientist can maintain a system like this very well. If you go for a kind of online system that has latency, there is kind of resilience and many other kind of constraints, you might need an engineer to kind of pair up for keeping the system running. Yeah, so great. I couldn't recommend more this model if you can afford it. Now, you might not have the means to afford it if you need to do something real time, right? Somebody has some real time information, then you need to react to that immediately. For this kind of scenarios, I would recommend serverless serving. Here's because the cloud providers have great free options on this with this configuration. So for Cloud Run is the let me give a step back and define serverless. Serverless means that you don't have a computer running all the time to kind of income requests to your model. You actually just start a new computer when you see that traffic is coming. So somebody is asking, then you might start your model at that moment when somebody is asking. That means that there is also like a delay in when you don't have a computer up and running, like around 10 seconds until you can get your results. But if you have frequent access, kind of that basically fades off because they keep the hardware on, warmed up to basically receive new requests. And yeah, in GCP, you can get 2 million free calls a month. And in AWS, you can get 1 million. So that's pretty a lot for many use cases. Though if your traffic is much bigger than that, then one needs, that can also get very expensive. So I would stay on the free tier as much as possible, but if not possible, then one needs to go to kind of online inference or reacting real time. And here I basically broke down some key players. There's GCP and put like some reference point on how that might cost. Like to get access to a 16 gigabytes T4 GPU, one need around $200 a month to keep that live 24/7. AWS, it's a little bit more expensive, although the GCP versus AWS price comparison can vary a lot depending on the resource you pick. So I wouldn't say there's clear cheaper option here. Then I added in the bottom also Hugging Face, as it's kind of a different player. They basically give you a very simple UI that you can swap between cloud providers and is already integrated to the rest of the stack. It's a little bit more expensive, like around 20-30%. But the usability is just so much better. The other cloud providers, they kind of have very advanced features, but also means you have to have a lot of involvement to set everything up in the way it should be done. Yeah, basically another trade-off between cloud providers you can see is GCP is very advanced in data and AI, while kind of AWS is the most established, biggest market share and kind of most options and fine-tuning possibilities. So the other cloud providers, I didn't mention because they don't have anything that they stand for, but they can also be interested if one finds kind of opportunity there. Yeah. So moving on, if I would have to make a recommendation on what would be a good stack that would be cost-effective, free ideally, would be basically one uses notebooks in Colab, uses a lot of Hugging Face. There has a lot of stuff for free there, data model versioning for one. And then going into serving direction, prefer first batch if you can, no added costs. Then there is also this app serving via Hugging Face. There is kind of a GPU with 16 gigabytes, is also free. And there you don't, it's not like only an endpoint where you can call your model, it's like a UI, but you can serve your model from that UI and basically call it and get results. So that's also a competitive option. If you need then to go a little bit more complex, but still stay on the free side of things, there is the serverless serving. From there on, then basically, I would probably, given that there are so many things already in GCP, I would probably continue investing on the GCP side of things. I don't know, there's no clear winner there from cloud providers. I think it's more important that you have less kind of things in parallel. If you have two clouds, there is a cost in maintaining that as well. Yeah, that's basically the recommendation. The other thing I would like to highlight is this grants for NGOs and students. They have different tiers and options, like the AWS option offers up to 5K for 12 months, but they also take an admin fee, so that's maybe not the best. So like for the 5K option, you have to pay 500 euros entrance, so it's not very, the trade-off is not so clear. Yeah, and if you're going for the startup direction, there is much bigger amount. Yeah, if one, I mean, as I hinted before, price-wise, like 1K, 2K can go very fast out. So if this is the only budget of our organization, have to run a lot of kind of machine learning, one has to be nevertheless very careful to not go over these price margins. Yes, and last thing from my side is like this case study. I mean, GetYourGuide, we wanted to improve the onboarding experience of suppliers. They usually have some content for the activity they want to onboard, but that content doesn't meet our requirements. We want a specific tone of voice. We want to highlight specific things. So let's use a LLM to get this kind of raw input from suppliers and transform it into kind of something that we are comfortable with displaying to our marketplace. That's the task. For that, we tested like LLMs and Llama, and one side 13B, the other side was OpenAI. Here is more or less the key parts of the code that one needs to do to fine-tune Llama. As Marina hinted, there is like the LoRa part with quantization. There is also STF trainer, which is a component for Hugging Face. Yeah, I want to go to deep here though. Some of the key learnings of this project was, I mean, we did define a criteria of human evaluation, and GTP was slightly better than Llama 13B, but not too much better. Fine-tuning in OpenAI can get very expensive. Like you can be literally like one click away of a 300 euros increase in your spend, and every time you want to rerun your fine-tuning, that can also goes to a queue and can take a long time. It's also not customizable. Like if you look into the slide before, with so much hyperparameters one can kind of customize, here you have very few control. And there was also like they deprecated actually the fine-tuning API and services that they were providing for us in December. So meant also that we have to retrain all our models in the new API. So that was something that in open source, if you own your infrastructure, you don't have to worry about. On the other hand, like serving this model 24/7 at scale, the cost of starting it was too high for this project, which was super low traffic. So we opted to go to production now with the OpenAI version of this model, but in the future we can also re-evaluate it. Yes, and now I'll move to Marina for the conclusion.
Thank you, Jean. If we were to summarize our main ideas in a few bullet points, is that it's important to validate your training approach first and to start simple. Then to save on training and inference costs, take advantage of model compression methods. Choose the simplest way that you possibly can to go to production, because the configuration of the inference is probably the most challenging part of this whole journey. And you use exactly as big of a hardware as you need and as big of a model that you need. And that can both help you save on your compute and on your compute costs, but also importantly, it leads to lower carbon footprint. And just to conclude that, of course, it is very challenging to work with big NLP models, and especially with LLMs on a budget. And especially it's challenging to go from trying things, which might be relatively easy, to building something that is production quality. But we hope that some of the ideas that we brought to discussion today, and some of the things maybe that you can share with us, could make it easier, and then the progress in the field can make it even more possible to deliver value while not spending too much money. Thank you. Then I think we can also go to the discussion.
Yes.
Thanks a lot.
Thank you so much, the two of you. This was an amazing talk. Maybe we can all send some applause emojis here in Zoom.